In order to transmit the information over the media, the transmission media, we need to encode the information. And then we need to remember that there are different levels of encoding. For instance, the source code encoding, when we map the source data to binary data, reducing redundancy prior to transmit the information across the network. The channel encoding, that is when we add to the source information redundancy, for instance, in order to detect errors and implement some kind of retransmission technique method. And finally, the line coding or modulation coding, when we assign the data to the symbols that will be transmitted across the media. And then we will pay attention. We will focus our attention on this coding, the line coding or the modulation coding, but particularly in order to understand how Ethernet transmits the information, we focus our attention on the line coding, that is using typically the baseband of the media. And then remember, this scheme illustrates what was used previously to transmit information across the analog telephone network, that is transmit information across the voice channels using typically modems. We could use modems too, for instance, when we transmit the information, but over a carrier, in order to use some spectrum of the radio frequency propagation, typically. For instance, in the case of some transmissions, for instance, using wireless medias. But now we will focus our attention in this particular case. That is, here we are channels, typically, for instance, twisted pair, coax, fiber, an optical fiber. Then we need to encode the data, the source data, the source information, and in order to transmit that information serially. Remember that serially, not in parallel, across the media, the transmission media. During the transmission across the media, some interference could happen. Then we need to face that particular event using an appropriate encoding in order to detect correctly the information received in the receiver side of the transmission. Then remember, we could transmit across baseband transmission, typically the transmission of a digital or analog signal directly over the transmission medium without modulation. That is, the signal is transmitted in the original frequency range. Typically is what we use in the Ethernet links, or carrier-based transmission, when the transmission of signals is performed using modulation methods. And the modulation methods permit that the signal were transmitted in the frequency range of the carrier. Typically, when we use some spectrum of radio frequencies, for instance, to transmit across the wireless media. Well, in order to understand the line coding, in fact, we could use different symbols. For instance, a symbol could be, in the case, for instance, of this encoding method called frequency shift keying. We could use different frequencies for each symbol. This is one possible coding. Another possible coding is typically to transmit voltage levels, like in this encoding. For instance, in this case, we could use, for instance, with each time we need to transmit 0, we don't change the level, the voltage level of the media. But when we need to transmit 1, we could perform a change in the signal in the media, and this type of coding is called RZ, that is return to 0. Those are other examples of different digital line codes. For this bit stream, we could code, for instance, using for a non-return to 0 coding and NRZ, then a typical voltage to represent 1, and another typical voltage to represent 0. And in that way, we could represent the information in that way. There are other possible codings, for instance, NRZ invert. We will see the detail, but typically when we need to transmit 1, we perform a change in the middle of the bit, and when we need to transmit 0, we don't perform the change of the voltage level, and in that way we could send this bit stream differently than, for instance, with NRZ. Those codings could be used in different line codings. Another example is Manchester, where typically we could use, for instance, that for when we need to transmit 1, we perform a transition from one voltage to the other, for instance, in this way. But when we need to transmit 0, we perform a change, but in the other way. And in that way, we could transmit information, performing always a transition, at least a transition per bit, or perhaps 2 transitions per bit. Or, for instance, in the case of bipolar encoding, that is represented here, where we change from positive voltage to 0, or from 0 to negative voltage, or from a negative voltage to 0, and so on. But the changes are performed only if we need to transmit 1. If we need to transmit 0, we don't perform any change in the line. Those are typically different line codings. Then, in order, for instance, to understand the encoding used in the Ethernet technologies, we need to remember that Ethernet has evolved from the original 10 megabit per second copper-based technology to 100 megabits, then 1 gigabit, then 10 gigabits, and so on, fiber-based technologies. In order to transport digital bits of data across any medium, various issues need to be considered. The first is the bit transmission speed. The second is the frequency of the carrier wave, in order that the frequency could be propagated across the media. The signal to noise ratio, the component of DC, of continuous current, and the clocking. For each Ethernet technology, particular encoding techniques were developed such that data could be transmitted across the medium with the greatest efficiency. The idea is to be able to transmit the faster information rate using the same particular media with a particular bandwidth. And then here we are, different encoding mechanism used in the different Ethernet technologies. Then for the case of 10 megabits legacy Ethernet, we use Manchester encoding. It was one of the first encoding techniques used to transmit information across typically local area network Ethernets using Ethernet. Or for instance, the encoding used in 100 megabit fast Ethernet, for instance, 4B, 5B with MLT3 encoding. In the case of 100 base TX. In the case of 100 base FX, the use of 4B, 5B encoding using NRZ-E encoding. Or in the case of 1 gigabit Ethernet, we could use those encodings. And finally, in the case of 10 gigabit Ethernet, the use of those encoding mechanism or techniques. We will see with deeper focus some of those encoding techniques, typically Manchester and NRZ-E, 4B, 5B, MLT3, and PAM. Then, in the case of non-return to zero encoding, here we are typically a bit stream. The NRZ encoding is one of the simplest encoding methods. The method uses one voltage for logical zero, for example, 0 volt, and another voltage, for instance, plus 0.5 volts for a logic 1 data bit. The physical parameter used to implement the symbol associated with the 0 or the 1 depends on the typical media used. It's not the same in the case of copper twisted pair cable, or for instance fiber, or radio frequency in order to propagate a radio signal, a radio frequency signal across, for instance, the air or the vacuum. There is a problem with the NRZ encoding method. When data is transmitted, there could be lots of ones or lots of zeros in sequence. For instance, a lot of zeros could be seen as a continue signal of 0 volts, for instance, or a continuous stream of ones could be seen as a continuous signal of plus 0.5 volts. When there are long runs of bits that are the same, there are no voltage level transitions, making it difficult for the receiving station to know if it is clocking the signal correctly and so deducing the correct number of bits. For instance, a stream of 0 or a stream of ones, the receiver is aware that is a stream of ones or is a stream of zeros, but there could be errors in the number of bits detected. Then this is a typical problem called clocking. We need to, in the receiver side, we need to be sure in which moment we need to sample the signal in order to establish if it is a 0 or if it is a 1. Since it can be difficult for a receiving station to know if it is correctly detecting the boundaries of each bit with the NRZ method, other encoding methods are more often used on digital communication. Sometimes, for instance, we use NRZ encoding, but with another encoding method in order to force transitions in order to obtain self-clocking, what we called self-clocking codes or self-clocking encoding. Well, then the clocking. When bits are sent from a sender to a receiver across a network, they need a mechanism to synchronize their clocks, because the clock of the transmitter and the clock of the receiver it could be different, slightly different, but different. Then in a very long bit stream, we could in the receiver side we could perform an error in the detection of the bit stream. So they both know when a bit starts and when it stops. This means that clocking information needs to be sent as well as the data, so that the receiving station can synchronize its own clock with the sender's clock. Synchronous connections, for instance, HDLC point-to-point links, use a separate clocking line to transmit clocking for information. If a clocking signal is used along with the data signal, it is much easier to deduce where one bit starts and ends. And then this is the case in synchronous transmissions, like, for instance, the transmission used in HDLC links. However, some technologies like Ethernet don't have a separate line that could be used to send clocking information. One of the reasons is that typically Ethernet is a transmission point to multi-point. Then it's very difficult to transmit a separate clocking line to all the possible destinations. Some encoding schemes can send clocking information within the data signal itself without the need to send an additional clock pulse. Those are self-clocking encoding schemes. Then we will see in that kind of encoding schemes that are called self-clocking encoding schemes. Then the first one is Manchester encoding. Remember, Manchester encoding is used in 10 megabit legacy Ethernet. In Manchester encoding, pay attention to this bit stream and the waveform of the digital signal. To send a logic 0 data bit, decrease the voltage down in the middle of the bit period. To send a logic 1 data bit, increase the voltage up in the middle of the bit period. It's not important if this signal, this waveform, corresponds with voltage change or another physical parameter that change. What is important is that the symbol change, the symbol used change in the middle of the bit in that way, decreasing or increasing. Advantage, always there is a voltage level transition in the middle of each bit time. Remember, this is the bit time. And in the middle of the bit time, we transmit a transition, a voltage level transition. Thus, Manchester encoding is effectively self-clocking. That is, always there is always at least a transition in each bit time, and perhaps when, for instance, there is a train of same bits, for instance, a train of zeros or a train of ones, there are two transitions per bit time. Then the conclusion is a separate clock signal is not required, and there are no long strings of logic 0 or logic 1 levels to cause the clock to drift. Disadvantages or disadvantage is when a series of alternating zeros and ones are sent, the frequency of the signal is equal to the bit rate. But when a series of zeros or ones are sent, that is only zeros or only ones, an extra transition occurs between each bit. The frequency of the signal could be twice double the bit rate. Then the frequency may reach twice that of NRZ. In the case of NRZ, the frequency could be at most equivalent to 1 cycle per 2 bits time. In the case of Manchester, the frequency could be typically 1 cycle per bit time. Remember that particularity of the Manchester encoding. Then remember, Manchester encoding is used on legacy 10 megabits Ethernet networks. This is one of the most popular encoding techniques, but the problem is that we don't use optimally the bandwidth offered by the media. RZE encoding. To send a logic 1 data bit, invert the voltage state from whatever it was before in the middle of the bit period. This is a transition. This is another transition. But when we need to send a logic 0, we leave the voltage state as it is. In this case, in this case, in this case, in those cases, we leave the voltage state as it is. Non-return to 0 inverted is an encoding method, a method used on fast Ethernet 100 base FX networks. We typically use this encoding, but we use this encoding combined with another encoding that we will see now, that is the 4B, 5B encoding. Why because the problem of NRZ-E encoding is that is not self-clocking. Then typically the characteristics of signal codes are that they need to be typically DC freedom, that is without continue current component, continue voltage. Transmission of the clock signal is not necessary. We need to use some kind of self-clocking coding, and those are the known signal codes: NRZ, RZ, Manchester, AMI, HDV3. Well, for instance, NRZ and RZ are not self-clocking. We already see that. They are not DC free. That is, for instance, a long run of bits in 0 or bits in 1 represent typically a DC component in the signal. And instead of that, for instance, we could realize that Manchester coding used in 10 megabits Ethernet is DC free, because always there is transition each bit time, and self-clocking. That is, the Manchester encoding is one of the typical signal codings that are that present the characteristics, the desired characteristics of the line encoding. AMI, alternate mark inversion, is a 3-level encoding. Is DC free, but is not self-clocking. Then we need to use AMI with another technique that permits to transmit typically some transition in order to provide clocking. And then remember that, for instance, typically we could use NRZ-E combined with 4B, 5B. Why? Because 4B, 5B provide the self-clocking that NRZ-E lack. Then characteristics and then of digital cable codes, cycle recovery. What the Manchester processes have in common is that they allow the clock to be recovered from the signal. However, the Manchester procedures require twice as much bandwidth for transmission as, for example, the NRZ code. Is what we could see in the explanation of NRZ and the explanation of Manchester coding. The NRZ code doesn't allow clock recovery, it's not self-clocking, as unfavorable bit consequences may not cause a state change for a long time. Therefore, this code is only useful if a bit conversion is done beforehand. A bit conversion, like, for instance, 4B, 5B conversion. This is achieved, for example, by the 4B, 5B conversion, where we add a fifth bit in order to code the same information. The same information that is coded with 4 bits will be coded with 5 bits, and the combination of those 5 bits is a combination that has or at least a bit change. And in that way, we could use the combination of this coding with the NRZ coding to provide a particular self-clocking coding. Then, well, in well, when we transmit then 4B, 5B, in fact, remember that 4B is what we call a nibble, that is the half octet that is converted to 5 bits block in such a way that the maximum of 2 consecutive zeros occur in each 5-bit clock. Remember why 2 consecutive zeros? A maximum of 2 consecutive zeros, but because, for instance, in the case of 100 megabits, remember, in the case of 100 base FX, we use NRZD. Remember, NRZD don't perform any voltage change when we transmit zeros. Then the use of 4B, 5B avoid the use of more than 2 consecutive zeros. We will see that in some minutes. The example of then the example of 4B, 5B block code with well, in this case the use of MLT 3 line encoding at 100 megabits per second Ethernet over twisted pair. That is this is the other combination of encoding techniques. Then we'll see, for instance, 4B, 5B encoding and MLT3 line encoding. Well, when we use, for instance, a combination of encodings, for instance, in order to provide clocking to some non-self clocking codings, we could use this technique. The 4B, 5B code avoids long 0 or 1 sequences that could make clock recovery difficult. For this purpose, 4 data bits are encoded in 5 signal bits. There must be no more than 1 leading 0 and no more than 2 final zeros. That way, we avoid a long run of zeros in the bit stream that we transmit across the line. For instance, coded in NRZ, or in the case of this technology, MLT3. There are then 5 other codons. This is a nibble of 4 bits, and this is called a codon. That is a chunk of 5 bits. Pay attention that always any combination of codons present a maximum of 3 consecutive zeros. By adding redundancy, you only achieve an efficiency of 80%. Why? Because we transmit at, in fact, a particular bit rate that the transmission media supports, but we use, in fact, only 4 bits are useful from each codon of 5 bits. That is 4/5. That is 80% of efficiency. In the case of, for instance, the coding used by we say previously 100 base TX, we could use the combination of 4B, 5B with this multi-level transmission encoding that uses 3 levels. That is the MLT3 multi-level transmission encoding is a line code with 3 voltage levels. The positive voltage, 0, and a negative voltage. MLT3 changes the signal level for a logical one in the data stream, whereby the next level in the sequence is always 0 plus, that is a positive voltage, 0, a negative voltage, 0, a positive voltage, 0, a negative voltage used. That is always, there is a sequence of positive 0, negative 0, positive 0. At logical 0, the signal level remains the same. MLT3 is comparable to the binary line code NRZE by using n equal 3 symmetrical stages. Remember that the logarithm of in base 2 of 3 is what we use to convert the number of stages in the number of bits. Then the DC share, and that is there is no DC. Always the transition is produce a DC component 0, and the bandwidths are reduced to this one, the log in base 2 of 3. Remember, 3 is the number of stages or a level of quantization levels. That is the number of different possible symbols, a positive voltage, 0, and a negative voltage. And the logarithm of in base 2 of 3 is 1.59. Then we underuse a little bit the media. But this permits to in fact to transmit with less intersymbol interferences. Blocks, then, for instance, in this example, we transmit this bit stream, and we convert this bit stream using 4B, 5V in this bit stream. Then this bit stream always present transition, at least a transition each codon transmitted, at least one transition. And finally, PAM, that is pulse amplitude modulation, is another encoding technique used typically in gigabit Ethernet. Remember, gigabit Ethernet. Gigabit Ethernet, we use PAM encoding, but combined with this kind of another encoding that is similar to 4B, 5B. But in this example, we could see that PAM5 is the modulation method used in this gigabit Ethernet technology, 1000 base T. It is a combination of pulse modulation and amplitude modulation. It is called pulse amplitude modulation with 5 stages per transmission step. Each step, the voltage level could be in one of those 5 voltage levels, and is by using 4 double wires. In the case of 1000 base T, we use the four pairs to transmit, in fact, 4 signals, 4 digital signals, each signal with 5 stages. Then each bit time we transmit a total of a combination of 20 stages, that is 2 to 20, or 5 to 4, that is 625 states per clock. That is, for instance, 8. It could be could transmit then, for instance, 8 bits, and we could use the other encoding technique to use the other combinations of states to convert this modulation, this encoding technique in a self-clocking technique. Then typically this is the shape, the waveform of the signal in the pairs, the twisted pairs used in gigabit Ethernet.